All right, thanks for the introduction. And I'd like to thank Kirti for awesome talk and setting up the platform for my talk. So I'll slice out the network telemetry piece from his talk and show you what is we at Princeton think about how network telemetry should change and evolve. So before I talk about what SONATA is, let's take a quick overview of what conventional network telemetry looks like. We have these network devices across the network. Then there are a bunch of protocols and tools that are used for collecting data from these monitoring sensors across the network. These tools can be NetFlow, packet capture, SFlow, etc. Right? So all this data is now collected to a storage or warehouse where you have compute resources over which the queries are executed, and you get answers, right? So conventional network telemetry now, as I show you here, can be divided into two stages. One is the collection, where you use the monitoring sensors. The other is the analysis. So notice that the analysis stage is driven by collection, but vice versa is not true. Like the collection is actually not driven by what analysis has been done on the network or the traffic. So I'll talk about what's the problem with that. So if this is the status quo of how network telemetry is done, the problems with this are of two types. One is about expressibility. As I mentioned, that since there are two different stages, if you're a network operator, you have to individually configure these two stages. That is, you have to figure out like what collection tool you have to use, and then among them, like how do you configure those devices to collect the data, and then based on your collection strategy, you choose how to analyze the data. These data collection tools and protocols are sometimes static and often coarse-grained. The analysis setup, because it is driven by your choice of collection tool, it's kind of brittle. So it's very hard, once I logged in with the type of collection tool I want to deploy in my network, it's very hard for me to kind of like make a decision. I want to change how I want to collect the data. Just to give you an example, the nature of queries can be very diverse, and not all collection types can fit the different queries that you want to run in the network. Be more specific, you can choose to do packet capture across the network and answer very fine-grained queries, but at the same time, that is too much of data to process and analyze. So you might go on with making a decision about using SFlow or NetFlow kind of tools to analyze the traffic at the flow level. So there is either too much of data or too less of data, and that kind of creates a problem with respect to expressibility, that you should know ahead of time what kind of analysis you want to do. The second challenge is in terms of scalability, that as the traffic volume increases or the number of monitoring queries or telemetry queries that you want to execute in the network increase, then it becomes very hard to answer these queries in real time. And that's the key if you want to build futuristic self-driven networks, or even in the current world, if you want to answer or solve problems in real time. You want these queries to be answered in real time, but like as the volume of traffic increases or the number of queries increases, it's very hard. Also, given this set of collection tools that you have across the network, it's very hard to transport the data from the collection to the storage warehouses. So to summarize the problem with the status quo of network telemetry, it is actually very hard to both express as well as scale these network telemetry tasks. So this is where SONATA comes into picture. So SONATA, in summary, is basically query-driven telemetry, and it's pivoted across around three ideas. So the first idea is uniform programming abstraction, where we allow network operators to express queries as data flow operations over packet tuples. The second idea is about query partitioning, that we observed that there are these reconfigurable and programmable devices across the networks that can be used to execute subset of data flow operations in data plane. And the third idea is iterative refinement, where we observed that the portion of traffic that satisfies the query is actually a very small subset of the total traffic. So we come up with this idea of iteratively zooming in on traffic of interest. I'm sorry. I'll grab some water so that I'm more clear with my pronunciation. All right. So the idea of SONATA is to kind of make it easier for network operators to express as well as scale the network telemetry queries that they have. So let's talk about the first idea. The first idea is about uniform programming abstraction. So the key problem, which I was talking about earlier, was like, because you have this plethora of collection tools that you have to make decision about and then configure them, So as a network operator, you have to be aware of where or how your query is going to get executed and how the data collection has to happen, which becomes cumbersome because you don't know ahead of time, like, what is the nature of query that you want to execute in the network, right? So the extensible packet tuple abstraction is that we provide the abstraction in which network operators can express queries over arbitrary fields or collection of arbitrary fields called tuples, and assuming that you can express these queries or execute these queries for any location in the network, any packet, any location in the network, right? The second aspect of this programming abstraction is the expressive data flow operations. We observed that most of the network telemetry tasks require collecting aggregate statistics over the subset of the traffic, and sometimes you want to do correlation and you want to join multiple streams or packet tuples together. So using or making a choice of declarative, like expressing your queries as declarative queries composed of data flow operators kind of makes it easier or makes it a natural choice of like what kind of programming language or abstraction you want to choose for expressing your queries. So I'll give a few examples to give you a more sense of, or a better sense of like what this uniform programming abstraction looks like. So let's take a very simple example. It's a security application where you want to detect traffic anomalies in the network. The anomaly is tuned to, which is very common for the reflection attacks, in which there are too many source IPs sending traffic to a particular victim, right? I call it potential victim because that might not be the only feature you want to extract to confirm presence of such an attack. So you express the query over packet stream, and packet stream can be arbitrary collection of tuples, which can be headers, payloads, or the context of the packet, right? So on that packet stream, you specify the window over which you want to apply these reduction kind of operations. And the first operator you apply is basically a filter, which does packet.source-port, which is part of the packet's header field. You make sure that you're looking on the DNS responses. And then you do a map operation where you kind of like extract out the destination and the like pair of destination and source IPs. And you apply a distinct operation in which you get the unique pairs of these destination and source IPs. And then you apply another map operation to kind of like ignore, because you're not interested in what the exact source IP is, but you're interested in how many unique source IPs are. So you apply another map, then you apply another reduce, and then you finally apply a filter in which if the number of source IPs sending traffic to a particular host exceeds a pre-specified threshold, then you report that destination IP. So this is a simple way in which you can express your query. So notice here that you don't have to worry about where exactly this query is going to get executed in the network and how is it going to get executed. So network operator is abstracted away from these complexities and details. All they have to worry about, like on the packet, what header fields you are interested in, express the query that way. Another example is if you want to confirm this reflection attack, and so you want to detect hosts which showed the traffic anomalies and are of the type RSig, right? So it's a very simple transformation. The key operator to notice here is the join operation, in which from the previous transformation, I was able to extract the potential victim IPs, and I join it with the packet stream again, and then apply a filter checking if it's of the type RRSig, right? And if it like, do some map reduce, get a sense of like whether it exceeds a pre-specified threshold or not, and report the destination IPs. So the key takeaway here is like, with this kind of programming abstraction, it is actually possible for you to combine or join multiple packet stream, like analysis over multiple packet streams together. So does it change the status quo? In terms of expressibility, yes, it does, because now you can express the data flow queries over packet tuples, so you don't have to worry about like the low-level configurations. You're not tied to the low-level APIs or platform-specific APIs that you were using for collecting data, or because now you're not locking in or you're not differentiating between collection and analysis. So you're not, it's kind of less brittle or very flexible in a sense that it's very trivial now to add new queries on the fly or change the collection tools completely, right? So it is now easier to express network telemetry tasks if we go with this programming abstraction. The second question is like, how do you execute queries expressed this way, right? So a natural candidate, because the data flow programming abstraction or paradigm is more suited to stream processors or the state-of-art stream processor. When I say stream processor, I'm referring to something like Apache Spark or Storm, some other tools. And a naive solution can be that, okay, if you express queries with this level of flexibility and programmability, what if you basically process all or subset of traffic collected from the network, send it to a state-of-art stream processor, and let the magic work, right? So this sounds like an excellent solution, but at the scale at which these networks operate, specifically if I talk about a large exchange point, for example, the exchange traffic at the rate of few terabits per second, these stream processors are actually not designed to handle traffic at that scale, right? So these solutions can be expressible to let you express policies the way we were talking about, but sending all the traffic to stream processor is not a scalable solution. So let's talk about how Sonata makes things work and scale the solution, scale query execution. So there are two key ideas here for scaling the query execution. One is about query partitioning. The second is about iterative refinement. So when I say query partitioning, the idea is that we observe that there are these programmable devices across the network. You can call them SDN, or I call them just reconfigurable or programmable devices in the network. The idea is that they can actually execute subset of the data flow operations that you express or the network operator expressed. And this reduces the packet tuples at the cost of, like, you might require some additional state in the network. And the second idea is about iterative refinement, that we iteratively zoom in on traffic of interest, reducing the state at the cost of additional delay. So I'll talk about it in more detail. Let's start with the query partitioning. So the key observation here is that data plane can actually process packets at line rate, right? So this is a capability that is relatively unique compared to the other use cases of stream processing, that you have a data plane that can process packets at line rate. So how it works is, like, you can execute, if you have the targets or the data plane targets are of using something like OpenFlow, so it's kind of easier for you to apply transformations or the data flow operations like filter and sampling in the data plane, which are relatively simple but effective. The second set of hardware devices or the targets that I'm talking about are PISA-based, which is the protocol independent switch architecture, which uses P4S programming language. So in addition to filter and sample, you can actually do flexible map, reduce, and distinct operation in the data plane. So the trade-off is that you trade packet processing costs with the additional state in the network, in the data plane. So I'll make a point about PISA targets for query partitioning, because that's what we use for building, or that's the prime thing which we use for building the prototype of Sonata. So there are 4 key aspects of PISA switches or PISA targets that allow us to effectively do query partitioning. One is that it enables programmable parsing, that you can have like new query-specific header fields that you can define on the fly, and you can parse and deparse those header fields. Second is, like, you can carry state in the packets and also maintain state in the network devices, the hardware itself. And third is the customizable hash functions, that it supports hashed functions over flexible set of fields that you can define programmatically. And finally, the flexible match action tables, which kind of, like, you can define the order in which these match action tables have to be applied, and like support match action tables with these programmable actions. So using these kind of hardware or targets, it is kind of like now straightforward, relatively straightforward for compiling data flow operators in the data plane. Executing map, filter, and sample is relatively easy, because all you have to do is, like, apply the sequence of match action tables in which you can figure out, like, what header fields you want to apply a map operation on, or how you want to filter and sample there. Distinct and reduce are relatively complex. So the way it works is, when the packet comes in, you basically compute the index in the hash table for which you have to update. You read the index value to the packet's header, then apply the transformations, and then update the, write back the updated value to the hash table. And the packet goes on with the updated state. And then you apply different transformations on the packet, which has all these state captured from the hash tables itself. So in addition to applying just these normal hash tables, we actually also explored the idea of using sketches in the data plane, which is not a new idea, but directly transforming these map reduce operations into these sketches that we can apply in the data plane was very exciting. And we were actually able to implement these reduce operations with like the function, transformation function is sum, as count min sketches, and distinct operation as basically Bloom filters. And we are also currently exploring how we can use hyperlog plus sketches here. There are, of course, limitations in terms of what all you can do in the data plane. So we cannot do complex transformation like applying log on the stream of data packets here. Also, we cannot do regex in the data plane. So it's not important that we have to do everything in the data plane. It's important that we can do some subset of the data flow transformations or operations in the data plane. So just to give you a sense of like how query partitioning works in action, as the network operator expresses the queries to the runtime, runtime basically decides what data flow operations have to be partitioned and executed in the data plane itself. It compiles those data flow operators to the configurations with the network data plane or the data plane can understand. And when the packet comes in, it first applies those transformations to the data plane itself, and then the transform packet tuples are sent to the stream processor. So note that like if we have these PISA targets, what we actually are able to do is like whatever is the computed state, each packet can carry that state as an additional header field to the stream processor. If the payload is not required, we can just prune that information from the packet, and then that information can go to the stream processor for the remainder of the transformations. So let's talk about the other idea, which is iterative refinement. So the key observation that we made was that there is only a small fraction of traffic that satisfies most of the monitoring queries. Just to give you a sense, like if you're talking about the DDoS query that we were talking about, I observed that for a large exchange point traffic data, and we observed like whenever there is an attack, it's usually 1% of the traffic that is satisfying the query. So with that observation, we were exploring like, is there a better way in which we can make efficient use of the available resources? And so we came up with this idea of iterative refinement, in which what we do is like we augment the operator's query to observe traffic at coarser level of granularity. And when we observe something interesting at the coarser level, then we winnow out things that are uninteresting or that don't satisfy the query at the coarser level, and iteratively zoom in on portions of traffic that were identified as interesting, iteratively zoom in and figure out like what is the portion of traffic that is satisfying the query. So there is, of course, a trade-off here, because like you are able to reduce the amount of packets that have to be, or amount of state that you have to maintain the data plane, or the number of packets that the stream processor has to process. But at the same time, this comes at the cost that when you're doing iterative refinement, it requires an additional delay that you zoom in from coarser level to finer and finer refinement level, right? So there is a natural trade-off here. So just to give you a sense of like how iterative refinement works in action, is like once the query has been expressed, once the data plane configurations have been updated, when the packet comes in, the packet tuples are reported to the stream processor. The output of stream processor goes back to the runtime that updates or that helps runtime to make decisions, or like for the next window interval, what should be the next configuration for the data plane and the stream processor itself. So notice that like initially I made a comment that the current state of art is such that the collection is not driven by analysis. Now in this, using this idea of iterative refinement, the key takeaway here is that like collection is actually now driven by analysis, that the output of the stream processor, output of your analysis kind of like sent back as feedback to the runtime, and it reconfigures the data pipelines so that like your collection is actually, like whatever you deem or you find as interesting is actually processed in the next window intervals. So we talked about two ideas of query partitioning and iterative refinement for scalable query execution. The key question here is like, there are different ways in which I can partition the query and refine the query, right? So if I take the example of the traffic anomaly query that I discussed earlier, so I can partition it at coarser level, say /8/16, or something, and there can be multiple levels in which I do this iterative refinement, right? So there are different choices that I have in terms of how I want to do iterative refinement, how I can do query partitioning. So the question is like, how do you select what is the best plan for a particular query, right? So let's take a simple example to get a sense of like how query planning works. So going back to the traffic anomaly query, just for reference, this is the query that we talked about, that you apply a bunch of map reduce operations on the packet stream. We take a very simple case for illustration here, that the partitioning plans are just binary. That is, either you execute all these operations on the data plane, or you execute all these operations on stream processor, right? And the refinement plans are such that the refinement key, the key on which you are applying this iterative refinement, is the destination IP. And the refinement levels that I want to consider is like /8 and /32, right? So let's see how the query planning works. So we came up with this abstraction of like expressing these different plans as a query plan graph. And the source is basically like all traffic. And there are two ways in which I can run this if I'm running it as at the /32 or the finest level of granularity itself, that I execute either this query completely in the stream processor or completely in the data plane, right? And then that's the finest level of granularity, so there is nothing else to do here, right? The other option is that I can actually execute this query at /8 first. And again, executing this query at /8, there are two options that I do completely in the data plane or I do completely in the stream processor. And then I move to /32, that is the finest level of granularity. And again, there I have two choices. So if you notice here, there are like 6 different ways in which you can execute the query. So how do you select what is the best plan? So what we rely on currently is that we use training data to enumerate the weights here, right? So the weights here are normalized value of the amount of packets that are processed, or number of packets that are processed by the stream processor, or the amount of state that is required in the data plane. So that's a normalized collection of these two different cost metrics, and you can, this is tunable, so you can, whatever is more important to you, if the resources of the data plane are more scarce, then you can tune the normalized parameter accordingly. But that weighted cost, the sum of weighted cost should be minimum, and that's how we select the query plan here. So in this example, I'm selecting /8 and then going to /32. But notice that when I'm using /8, then I'm executing everything in data plane. And for /32, after applying all those filters, it kind of makes sense to execute the query in the stream processor itself. So talking about the implementation or the architecture, so Sonata has 3 key components. One is the application interface, where the network operators are expressing the queries without worrying about where and how those queries are going to get executed. Then there is this runtime system, of the brain of this system, which basically takes some training data, takes the input from the operators, and then enumerates different query plans, and then applies those Dijkstra algorithm, the query plan graph, to figure out what is the best query plan for this query. And then finally, we have these data plane and streaming drivers. So these drivers compile the input queries which are which are sent to them as Dataflow queries into the target-specific configuration. So if I have a PISA target, then they will translate that to a P4 program. If I have an open flow target, then it will translate to a bunch of match action rules. Similarly, the streaming drivers, currently we are using Apache Spark, but that can be replaced by something else that is well suited for your application. So let's get more visual about how the implementation or how the system works. So the first state, the network operators express their telemetry task as the Sonata queries using the API that we expose. Then these queries are sent to the runtime, which basically takes into consideration the different queries together, and also takes training data into consideration to figure out what's the best plan for executing the query. Once the plan for each query is decided, then it sends these data flow queries, which take into consideration the partitioning and refinement, to data plane and the streaming driver. So that's query partitioning for you. And then these data plane drivers send the configuration to the data plane and the stream processor. So when the packet comes in, bunch of data flow transformations, map reduce operations are executed in the data plane itself. And then the normal packet goes out. So we only focus on mirroring out as less possible packets here. And on those mirrored packets, we have these transformations applied. And the traffic or the packets going to the stream processor have a minimal information that is required at the stream processor to complete the query. So the output of stream processor goes back to the runtime here with the query ID specified, so that runtime knows which query's output is this answer. And then runtime, again, updates the data plane driver and updates the streaming driver. So the key takeaway or the key message that I was trying to make was currently the collection is not driven by analysis, but the way we were building this system is we want to make it easier to express and scale, but at the same time focus on this key concept that collection should be driven from analysis. So I'll quickly talk about the evaluation of this work. Just to get a sense of this is not just fluff idea. We actually implemented and tested the idea over real world traces. So we used a large IXP network, 2 hours of long IP fixed traces, and we selected queries which were header specific. So because the traffic or the data which we had was IP fixed data, so we couldn't apply queries that require payload processing. And we compared against 3 different approaches. So the first approach is in which we do query partitioning, but we only do filter and sample in the data plane because it's the open flow target. The second is we do query partitioning with the PISA target itself, but we don't do any iterative refinement. And third is we do iterative refinement, but it's fixed and static. So this graph basically kind of demonstrates the benefit of query partitioning. We have these 3 different applications results shown independently, and then all of them running together at the system. And the y-axis is basically the number of tuples that are processed by the stream processor. So as you can see, like compared to if you just do sample and filter at the data plane, compared to that, if you are able to do map reduce operations in the data plane itself. So we are able to reduce the number of packets processed by the stream processor. And the key takeaway is like executing stateful operations in the data plane reduces workload on the stream processor. The second is the benefit of iterative refinement, that we compare it against the solutions in which you don't either you don't do iterative refinement or you don't do any kind of learning, and you just have a static way of refining the query. And we show like the in terms of amount of state that is required at the data plane. And what we are able to show is like if you do iterative refinement, it reduces the state required by the data plane targets. So the other result is about the benefit of query planning. Just to, like this is very colorful graph, so just to give you a sense of, read each color in this graph as a different query plan, right? And the constraints here is like, you have the maximum state. You can specify like this is the maximum state I can support in the network in my data plane, and you can also specify this is the maximum packets I can process. And given those constraints, the Sonata can basically figure out like what's the best query plan for a particular application. So compared to all other approaches, what you need to, like the key takeaway here is like it can figure out different query plans under different constraints and effectively make best use of available resources. So once you specify the constraints in terms of what you can support on the network, Sonata can come up with a better query plan for each of those constraints. So getting back to the quest here is like we want to change how this status quo works. And we talked about the expressibility with the programming abstraction. With these two key ideas of partitioning and iterative refinement, we are now able to answer queries, hundreds of queries in real time for traffic volume as high as few TBPS. That's based on some of the evaluation that we have done. And it kind of like strikes a balance between the available resources. So the two resources that you have is the amount of state you can maintain in the data plane compared to the number of packets you can process at the stream processor. And the query planning aspect of Sonata basically comes up with a plan which makes, or which strikes the right balance between the two resources. So this solution is now expressible and scalable. So I'll summarize my talk saying that Sonata makes it easier to both express and scale network telemetry tasks. And the three key ideas around which Sonata is pivoted is uniform programming abstraction, which makes it easier for network operators to express their queries. And then we use two techniques, which is query partitioning and iterative refinement, to scale how this query execution works. So we actually have a running code. Feel free to go to our GitHub repo. There are a bunch of tutorials and demos that we have added there. Like the name of this website should be simpler. That's how we envisioned, and we got a more snazzy URL here. So if you go to this website, you will actually get to see a demo that I planned for today. It didn't work out logistically, but like feel free to go to that website and check out the demo that we have there. You will also find a link to a more detailed paper where I talk about all the details about how we execute and evaluate the system. So with that, I'll end the talk. I'll take questions now. Thank you.
Matt Petak, Yahoo. Very good talk. I noticed in there you're talking about collecting queries into your runtime, then passing them down to the data plane and making changes in the data plane as far as how the packets are processed through. If you've got different queries that have potentially conflicting requirements on the data plane, does the runtime deconflict those ahead of time, or do you potentially push down instructions into the data plane that may be trying to do conflicting operations on the packets?
So I think like at this point of time, we don't solve the conflicting problem right now, but that is definitely a possibility. So what we like currently do is that, or what we did was like we enumerated 10, 15 different applications that we can focus on and identify like if they're running independently, like what is the requirement in terms of how many updates have to be made and all those things. But like conflict is definitely a problem that we have not solved yet.
So if it's one person asking questions, it's great, but if 6 different operators want to do different things, you might have more of a challenge.
Say that again, I didn't.
So if one person is formulating the queries, it'll work well. But if you have 6 different network operators that want to ask different questions, they may need to talk to each other first before trying to do this.
So yes, I think like currently, since we didn't address it from research perspective, like how exactly, what kind of conflicts are possible and how things can work. So that's the state right now. But I think like that is something which is, so there are different other works or previous works that have kind of solved the problem from a different perspective. So we can take ideas from there and apply it here. But like that has not been done. So I don't want to overclaim here. But yes, I think that is like that can be automated. I don't see that network operators have to talk to each other before pushing their policies.
Cool, thank you.